Good afternoon. My name is Teodor Vernica. I am a research associate at the National Institute of Standards and Technology in the United States, and today I will be presenting our paper Linking Performance Data and Geospatial Information of Manufacturing Assets through Standard Representations. Emerging visualization modalities such as augmented reality and virtual reality are starting to play a key role in smart manufacturing. These technologies have already proven to have a significant impact on worker productivity, but they are still relatively expensive to implement due to a lack of automated development pipelines, requiring skilled developers for one-off solutions. As part of the Product Lifecycle Data Exploration and Visualization project at NIST, we are investigating how standards can reduce development costs and improve interoperability for industrial mixed reality solutions for smart manufacturing. When looking at these issues, we are working closely with existing efforts in organizations such as the Augmented Reality for Enterprise Alliance, of which we are a member. This figure shows a high-level overview of a typical pipeline for generating industrial visualization prototypes. The left side represents the digitization of real-world information, while the right-hand side represents the rendering and presentation modalities. In order to produce a meaningful user experience, it is vital to use domain-specific models represented in the middle of the figure. The dotted line represents human activity in the current landscape. The problem lies in a lack of automated approaches to bridge the gap between the domain-specific data and visualization modalities, often resulting in one-off, unscalable prototypes. We believe that standards could provide a solution to this problem. In this paper, we demonstrate the merger between two standards to create a model for spatial and temporal perspectives of a production system. For the spatial perspective, we leverage a standard developed by the Open Geospatial Consortium called Indoor GML. Indoor GML is an open data model encoded in XML format, focused on the semantic and topological modeling of indoor spaces. For the temporal perspective, we leveraged the MT-Connect specification, which is a standard semantic vocabulary for manufacturing equipment. By leveraging existing tools supporting Indoor GML, as well as the publicly available NIST SMS testbed, we built a standards-based model that combines the two perspectives for data visualization. The process workflow of our implementation begins with creating an Indoor GML representation of the NIST workshop, a contract manufacturer inside the NIST campus. In parallel, we connect to the NIST SMS testbed mentioned earlier, which provides near real-time MT-Connect data streaming from the machines operating in the NIST workshop. Additional materials are incorporated, such as digital models of the manufacturing assets, as well as manuals and specifications. The complete model is then brought into Unity using a custom Indoor GML parser. We derive two use cases from the same data integration process, but we anticipate additional use cases can be conceived. The first use case demonstrates the potential benefits of this integration for a workshop supervisor. Through the connection of the digital assets to their physical counterparts in near real time, we can color code machines according to their current status. Green for available, red, unavailable, or yellow, unknown. Note that many machines in the NIST shop are not yet digitized and are therefore yellow. Clicking on any of the machines brings up additional execution data in MT-Connect format. This would allow a supervisor to get an overview of the status of the shop at a glance, with the ability to get more fine-grained information as needed. While this is a simple example of color-coding machine availability, you can imagine other layers of information being presented similarly. The second use case aims to help with maintenance and inspection of production systems. In this scenario, a map-like view of the shop floor is presented on a tablet device. Users can get directions for the shortest path between two machines by selecting a start and end point. Additional information such as user manuals, machine specifications, and maintenance hints are presented once the user arrives at the specified destination. While our implementation does present some limitations, these can be addressed through future work. A first problem lies in the fact that indoor GML does not support the geometric representation of objects within a room, such as the machines in our case. For that purpose, indoor GML was designed to interface with other standards that can provide this functionality, such as OGC's CityGML. Even so, these standards were not designed to model manufacturing assets. Mobile assets such as tools and automated guided vehicles could be modeled using the building furniture class in CityGML, and semi-fixed assets such as the machines could be modeled using the int building furniture class, but this delimitation is not always clear. For a more robust implementation, the standard would need to be extended to include additional manufacturing concepts. Finally, while not the focus of this paper, the ideas and implementation presented here can have implications for mixed reality applications. We are currently exploring how these predefined geospatial models can be leveraged in industrial, AR and VR environments, and what affordances they might provide in terms of interoperability and development time saving. Additionally, as mentioned in the beginning of this presentation, we are keeping a close eye on other standardization efforts that could integrate within our work. One example of this is W3C's WebXR device API that aims to bring stable XR experiences to ubiquitous internet browsers. OGC's GeoPose will provide a standard way of describing the position and orientation of real and digital objects in space, such as the machines in our example, or even the workshop building. SensorThings API could provide a way to integrate geospatially tagged Internet of Things data into our models. And finally, the European Telecommunication Standards Institute proposes a standardized AR terminology that will provide a common way of describing experiences. It is important to note that all four of these standards are open. If you are interested, please join the conversation at our upcoming workshop called Merging Geospatial Technologies with Cross-Reality in the Context of Smart Manufacturing Systems. The workshop will be held virtually at IEEE ISMAR 2020, with speakers from a diverse background discussing ideas similar to those presented in this paper at the intersection between geospatial information science, mixed reality, and smart manufacturing. Thank you for your attention. If you want to find more information about the SMS testbed or about other mixed reality efforts at NIST, you can search for the terms below. We're looking forward to answering any questions.